The next topic I want to talk about is acceleration. And acceleration is one of those words that you have used in your everyday life, and it's partially right. And sometimes these are some of the hardest words to wrap your brain around, are words that you've already been using, but now I'm going to ask you to change the way you're using it. And with acceleration, I'm just going to ask you to add something to it. So I suspect that coming into this class, you would think of acceleration as, speeding up really quickly. Like, if you've used this word in your everyday life, you've probably used it in the context of, I accelerated away from that stoplight, or something like that. And the good news is that is absolutely an acceleration in physics class as well as in real life. In order to wrap our brains around the physics definition of acceleration, let's remember about speed and about velocity. Recall that speed is just how fast. Remember that it is a scalar, and so it has no direction. So speed is how fast, and velocity is how fast and in what direction. Since it includes a magnitude, how fast, and a direction, that makes it a vector. So velocity is a vector. Looking at these cars, even if they were all in a pack together and moving together, then this car and this car could very easily have the same speed, but different velocities. Same speed because they're traveling equally fast, different velocities because they're traveling in different directions. So velocity is how fast and in what direction. And an acceleration is a change in velocity. And so that change in velocity, it could be a change in speed. It could be speeding up or slowing down. I suspect that if you've used the word acceleration in your everyday life, you've used it to describe speeding up, right? This is sort of the everyday version of acceleration. In fact, in the vernacular, in the everyday language, we have a separate word for slowing down. We would say decelerate. And well, decelerate is a fantastic word, and if you say it to me, I will know that you mean slowing down. In physics, we don't actually need that word because speeding up and slowing down are both accelerations. Together, speeding up and slowing down, that's the rate of change of speed. But guess what? There's a third way that you could change your velocity. You could change your speed, but you can also change your direction. So that means that acceleration is speeding up, slowing down, or turning. To be a little mathier about it, acceleration is a change in velocity in a given time interval. Again, speeding up, slowing down, or turning. So, since it's a change in velocity in a change in time, that means that our acceleration is a change in velocity over change in time. It could be in the x direction or in the y direction. If it's in the y direction, it would be the change in the y velocity over a change in time. It is a compound unit. It is meters per second squared. And we should really interpret meters per second squared as meters per second per second. In other words, every second, how much are your meters per second changing? It is the rate of change of velocity. Again, those of you that have had some calculus will recognize this as the derivative. Since it is the rate of change of velocity, that means that the slope of the velocity versus time graph is the acceleration. And it is a vector. Because it's the rate of change of a vector, it itself is also a vector. So now we've encountered two vectors, velocity and acceleration. They both require a direction and a magnitude. Let's do a quick example. A Porsche goes from stop to 27 meters per second in 3.6 seconds. Well, a VW goes from stop to 27 meters per second in 24 seconds. So in this case, we have two cars. They have the exact same final velocity, but they have different times that it takes them to get to that final velocity. So we could just calculate their acceleration. A equals delta V over delta T. And so A for the Porsche, well, that is going to be delta V, 27 meters per second, minus 0 meters per second, to be real pedantic about it, divided by 3.6 seconds, minus 0 seconds. And when I run my calculator, I get 7.5 meters per second squared. Again, we can interpret this as the Porsche's velocity was changing by 7.5 meters per second every single second, or 7.5 meters per second squared. A for my VW, then, is going to be, again, 27 meters per second. Maybe I'll skip the subtract zeros on this one, in 24 seconds. And so this gives us an answer of 1.1 meters per second squared. Again, interpreting our units here, we can say that the VW, its velocity changes by 1.1 meters per second every second, whereas for the Porsche, its velocity changes by 7.5 meters per second every second. Okay, so we found their accelerations. What are their velocities at 1, 2, and 3 seconds? Well, we could just make a little chart here. But basically what we're going to be doing is rearranging this equation, and we're going to be rearranging it to say that delta V equals A times delta T. But let's just go ahead and make a little chart here. For the Porsche, we have velocity and time. Seconds, meters per second. Well, they were stopped at 0 seconds, so after 1 second, the Porsche would be going 7.5 meters per second. Again, that's what this meters per second business means. Well, if it's changing by 7.5 meters per second every single second, that means that after 1 more second, it'll be going 2 times 7.5 meters per second, or 15 meters per second. After 3 seconds, it'll be going another 7.5 meters per second greater, or 22.5. I got my units here twice. That's right. Okay, now let's do it for the VW. Once again, it stopped at 0 seconds. At 1 second, then it'll be going 1.1. After 2 seconds, it'll be going 2.2. And then I'll add another 1.1 to get to 3.3 after 3 seconds. So we see here that, again, the reason I'm doing this example is to just try and help us wrap our brains around these units, right? Every second, the speed increases by 7.5 meters per second. That's what that means. Every second, the speed increases by 1.1 meters per second. To use velocity and direction, every second, the velocity changes by positive 7.5 meters per second. Every second, the velocity changes by positive 1.1 meters per second. Okay, here I've given you a velocity versus time graph, and I'm asking you to sketch an acceleration versus time graph for this velocity graph. Why don't you try and do it on your own, and then catch back up with me, and I'll do it also. Okay, I've drawn my axes here. Let's look at this and see. Remember that I'm looking for the slope. The slope of this position versus time graph will give me the acceleration. Since this is the velocity in the x direction, the slope will give me the acceleration in the x direction. So let's look at what we see here. I see a positive slope here, and then it goes to a 0 slope before switching to a negative slope. It looks to me like we don't have units here, do we? But the positive slope is about 2, a rise of 2 and a run of 1. So the positive slope here is about 2, whereas the negative slope has a rise of about -2 and a run of about 2. So I see that the slope here is about half of what the slope is here, and in the opposite direction. So we're going to start off with a positive slope of about positive 2 in whatever units for about a second. And then it's going to be a slope of 0 for a couple of seconds. And again, we'll make this little dashed line to help guide our eye. And subsequently, we have a negative slope that should be twice as big as this. So maybe I should have given myself a little more room here. Must be down to about right there. Something like this for the last 2 seconds. Okay, there we go. There is my acceleration versus time graph for that given velocity versus time graph. Again, the acceleration is the slope of the velocity versus time graph. So something to notice is that the acceleration can be positive, negative, or 0. Well, let's look at this. When was the object speeding up? Well, the object was speeding up here in the beginning, and then it was moving at a constant speed, and then here it was slowing down, wasn't it? Because it's getting closer to the axis. So here we have a positive acceleration is speeding up. 0 acceleration is constant speed. Negative acceleration is slowing down. That's nice. That's nice. Unfortunately, it's not that tidy. This is one of the misconceptions that is challenging to get students to overcome. The idea that a positive acceleration means speeding up and a negative acceleration means slowing down. It's just not true. It really depends on the signs, right? And a positive acceleration is something that is moving in the positive direction and speeding up, whereas something moving in the negative direction and slowing down can also have a positive acceleration. And let me give you a quick example of that. So we just did that graph which I showed, where we did see that a positive acceleration was speeding up and a negative acceleration was slowing down. But what if instead I'd given you this velocity graph? Okay, there's a different velocity graph. Now, in this region right here, what is the object doing? Is it speeding up or slowing down? Well, remember that velocity is 0 here, so this might be 0 meters per second, and I don't know, this is 10 meters per second, right? It's in the negative direction. So this is an object that was going 0, and now it's going 10. Isn't that an object that's speeding up? Yeah, it's speeding up. It's just speeding up in that direction, right? So it's speeding up in the negative direction. But what's that slope, positive or negative? That's a negative slope, isn't it? So here we have a negative slope, but an object that's speeding up. We just have to be real careful. Positive acceleration means you're moving in the positive direction and speeding up, or in the negative direction and slowing down. A negative acceleration is moving in the positive direction and slowing down, or moving in the negative direction and speeding up. There's a lot of different ways you can wrap your brain around this. One thing that's worked for a lot of my students is, we know, and this is a bit of a silly mnemonic. I'm just going to throw it out there. If it doesn't work for you, let it just pass right on through. We know that 2 positive numbers multiplied by each other makes a positive number. 2 negative numbers multiplied makes a positive number. Whereas if you have a positive and a negative, you multiply them, you always get a negative, right? So if we think about speeding up as a positive, right, then we have positive and a positive makes a positive. A negative and a negative makes a positive. Whereas a positive and a negative makes a negative, and a negative and a positive makes a negative. Again, this requires us to sort of think of speeding up as positive and slowing down as negative. Okay, if it works for you, roll with it. If not, you'll figure out a different way to organize it in your brain, I'm sure. Let's practice this just a little bit. Here we see a motion diagram. Shows the motion of a particle along the x-axis. Is the acceleration positive, negative, or zero? Well, is it speeding up or slowing down? Definitely speeding up. Is it moving in the positive direction or the negative direction? It's moving in the positive direction. So this is an object that's moving in the positive direction, and it's speeding up. Therefore, this is a positive acceleration. How about this one? Okay, here we see an object moving in the positive direction. Is it speeding up or slowing down? This shows a particle that is slowing down, right? So here we see positive motion, slowing down. This must be a negative acceleration. How about this one? This shows a particle moving in the negative direction. Is it speeding up or slowing down? This one's a little tricky. It starts here, and it's heading in this direction. The arrows are long in the beginning and shorter at the end. So this is an object that's slowing down. An object moving in the negative direction and slowing down has a positive acceleration. How about this one? This is a particle that is moving in the negative direction and speeding up. That means the acceleration is negative. There's other ways to think about this too, right? Remember, the acceleration is the rate of change of velocity. And so this is a particle whose velocity is getting more negative. Oh, okay. So it should be a negative acceleration. That works. This is a particle whose velocity is getting less negative. Oh, it must be a positive acceleration. Different ways of wrapping your brain around.